Have you ever really thought about why a book sitting on a table feels totally permanent, but a pencil balanced perfectly on its tip feels, well, like it's just waiting for a reason to fall? I mean, they're both balanced, right? But something's clearly different. Today, we're going to dig into the physics behind that exact feeling.
Right, so let's use this image, a ball in a bowl versus a pencil on its tip. We just know these are different. One feels safe, secure, the other feels, super fragile. Well, physics gives us the exact words and ideas to explain why we feel that way. And the one big idea that connects both the safe ball and that shaky pencil is something called equilibrium. In physics, it's a beautifully simple concept. It's just a state where all the forces pushing and pulling on an object completely cancel each other out. The net force is zero. Zip. Okay, so what does that net force of zero actually mean for an object in the real world? Let's break it down. It basically means the object isn't accelerating. Its motion isn't changing one bit. So it's either totally still, like that pencil, or it's moving at a perfectly constant speed in a perfectly straight line. Like a puck gliding across an air hockey table with no friction. In either case, all the forces are in perfect balance. Now, here's where it gets really interesting, because it turns out not all equilibrium is the same. There are actually 3 totally different kinds of balance, and this is what explains the difference between our ball in the bowl and that pencil on its tip. And we can get our heads around all 3 types with one really simple, really powerful mental picture. Just imagine a little ball sitting on different parts of a wavy, curved track. This one visual tells the whole story. First, you've got stable equilibrium. That's the ball at the bottom of the bowl. If you give it a little nudge, gravity just pulls it right back where it started. It wants to be there. Then you've got unstable equilibrium. That's the ball balanced on the very peak of a hill. Yeah, it's balanced, but the tiniest nudge and whoosh, it's gone for good. And finally, there's neutral equilibrium. Put the ball on a totally flat surface, and it just doesn't care. Push it a little, and it just rolls to a new spot and is perfectly happy to stay there. So what's the deep down physics that decides if something's going to be stable, unstable, or neutral? Well, the secret lies in something we can't actually see, but it controls everything. It's called potential energy. Just think of potential energy as stored up energy, ready to be used. A boulder at the top of a hill has a ton of it. And one of the most fundamental rules in all of nature is that things, when left alone, will always try to move to a state of lower potential energy. It's why water flows downhill, not up. Okay, now here is the magic link. Force and potential energy are really just 2 sides of the same coin. This equation looks a little scary, but the idea is simple. The force something feels is all about how steeply its potential energy changes. The steeper the energy hill, the stronger the force pushing it downhill. It's that simple. So let's connect the dots. We know equilibrium happens when the force is 0. And we just learned that force is related to the steepness or slope of the potential energy. So, equilibrium must happen wherever the potential energy graph has a slope of 0. We're just looking for the flat spots on the graph, the very bottom of the valleys, the tippy tops of the peaks, and any perfectly flat stretches. This idea of flat spots is so powerful. It lets us create something called an energy landscape. Basically, a graph that lets us just see the stability of a system in a single glance. We can actually picture this graph as a real landscape. The up and down axis is how much energy something has, and the side-to-side axis is where it is. Any object on this landscape will always try to roll downhill to a spot with lower energy. So a point of stable equilibrium, that's going to be at the very bottom of an energy valley. It's a point of minimum potential energy. If you nudge the object, it has to climb up the walls of the valley, and it'll just roll right back down. It's basically trapped in a stable little energy well. And you can probably guess what's next. Unstable equilibrium is found at the very peak of an energy hill, a point of maximum potential energy. It can balance there for a moment, sure, but any little disturbance sends it rolling down the sides, getting further and further away. And finally, neutral equilibrium. Well, that's just a perfectly flat plateau on our energy landscape. Moving the object around doesn't change its energy at all, so it has absolutely no reason to prefer one spot over another. This brings up a really good question, though. What if our energy landscape has a bunch of valleys, but some are way deeper than others? Is a ball in one of the shallow valleys still considered stable? And the answer is, yeah, it is. Stability is a local thing. You only have to look at the area immediately around you. An object in a shallow valley is totally stable, relative to its surroundings. It's stable for now, anyway, as long as it doesn't get a big enough kick to push it over the nearby hill and down into an even deeper, more stable valley.
Looking at a graph is great and super intuitive, but what if you're a physicist and all you have is a math equation for the potential energy? How do you figure it all out then? Well, then you break out the big guns, calculus. Don't worry, it's actually a really slick three-step recipe. First, you use a derivative to find the force from the energy equation. Second, you set that force to 0 to find the exact locations of all the flat spots, your potential equilibrium points. And third, you check the curvature at each of those spots. And that third step is the whole ballgame. It uses something called the second derivative, which is basically a curvature detector. If the result is positive, the curve opens up like a valley. That's a minimum, so it's stable. If it's negative, the curve opens down like a peak. That's a maximum, so it's unstable. And if it's exactly 0, the curve is flat and you've got neutral equilibrium. It's a guaranteed test every time. And just when you think you've got it all figured out, the real world throws a curveball. It's totally possible for something to be stable in one direction, but unstable in another. The classic example is a ball resting in the middle of a horse's saddle. Front to back, it's in a valley, but side to side, it's on a peak. Wild, right? So the next time you see anything that's balanced, you'll know the secret isn't just about forces being 0. The real story is happening on that hidden landscape of potential energy. Is it sitting at the bottom of a stable valley? Is it perched precariously on an unstable peak? Or is it just chilling on a neutral plane? This constant push towards lower energy is one of the most fundamental drivers in the universe. Which leaves us with a huge, final question. If everything in nature is always trying to settle down, why is our universe so full of motion, energy, and constant, endless change?